The focus of this chapter is on conjugated pi systems, and so we're going to start off by looking at the simplest conjugated pi system, a conjugated diene. Alright, so what is a diene? Well, this is just a fancy way of saying an alkene with two double bonds. When we name alkenes, we end the name in ene, and so a diene, two double bonds. There are three types of dienes that we might be interested in. There's cumulated dienes, where the pi bonds are directly adjacent to one another. There's conjugated dienes, which is what we're going to be primarily interested in, and that's where the double bonds are separated by exactly one single bond. And then isolated dienes are when the double bonds are separated by two or more single bonds. So in this chapter, we're interested in conjugated pi systems. And what we mean by conjugated is when the double bonds are separated by exactly one single bond, we actually have a continuous network of p orbitals. And the pi electrons, the electrons that are in these pi orbitals, are spread out over the entire network. They're delocalized among all these carbons. In cumulated dienes, there is no conjugation because the pi bonds are perpendicular to one another, so we don't have this conjugated system. And when we have at least two single bonds separating the pi bonds, they're too far away, right? There's a gap, and so they don't form this delocalized system. And these conjugated systems, these delocalized systems, have some special properties, and that's why we have a chapter devoted to those. Alright, so as I've mentioned, the focus of this chapter is on conjugated systems and the special properties and reactivity associated with them. In the simple examples I've given so far, we've only had carbon atoms, but we can also have heteroatoms involved in these conjugated systems. Again, as long as the double bonds are just separated by one single bond, it's fine to have a nitrogen or an oxygen as part of the conjugated system. Alright, so how do we make dienes? Well, we make them, the easiest way to make them is the same way that we learned to make alkenes last chapter, and that's through elimination reactions. So if we have an alkyl halide, we hit it with a strong base, we can get an elimination reaction that will give us our diene. And we can either start with where we already have one double bond and we have one halogen, or we can start with two halogens. As long as they're on adjacent carbon atoms, we can make a conjugated diene. Now, the choice of using the tert butoxide as the base, this helps encourage E2 reactions, and it eliminates the possibility of getting an SN2 reaction. If we use something like NaOH on this molecule, right, we'd get primarily E2, but we get some SN2 competing. So by choosing a bulky base, that will eliminate even more of the potential SN2 products. So one of the first features that you notice about conjugated dienes is that the length of the single bond separating the two double bonds is shorter than we would expect for a typical carbon-carbon single bond. One way of explaining that is the fact that these two carbons, when we have the conjugated diene, are sp2 hybridized. Right? In this case of ethane, they're sp3 hybridized. Well, so why does that matter? So the more S character there is in these hybrid orbitals, the shorter the orbitals are, and so the shorter the sigma bonds that they make will be. The p orbitals are significantly longer than s orbitals, and so when we have an sp3 orbital, that mixes three p orbitals with one s orbital, so it's only 25% S character. When we go to an sp2 orbital, now we're mixing two p orbitals with one s orbital, so now it's up to 33% S character, and so it gets a little bit shorter, and so we'd expect the sigma bonds that it would make would be shorter than the sigma bonds made with an sp3 orbital. In the next video, or I guess in probably two videos from now, we'll talk about molecular orbital theory and give another explanation for why these sigma bonds in the conjugated dienes are shorter than we might expect. So probably an even more important property of conjugated dienes is their special stability. Conjugated dienes are more stable than non-conjugated alkenes. One way we can measure that is through the heats of hydration. So how much heat is given off when I convert the alkenes into an alkane? If I take two one butenes that just have one single bond versus 1,3-butadiene, we can see that the energy released when we hydrogenate the conjugated diene is less than the energy that is given off when we hydrate 2 of the 1-butenes. And so the difference in those hydration energies tells us how much more stable the conjugated diene is. And so you don't have to worry too much about this hydrogenation. I think the main take-home message from this slide is that conjugated dienes are extra special stable compared to regular alkenes. All right, the next thing we want to consider is the conformations of these conjugated dienes. So we know that it's possible to freely rotate around sigma bonds. So these two conformations don't represent different molecules. They're not different isomers. The same molecule is free to rotate around this single bond, and so then these are just two different arrangements of 1,3-butadiene. And we call these S-cis and S-trans. So they're not like cis and trans when we have cis and trans in regular alkenes, right? Because that is how things are arranged around a double bond, which we can't rotate around. So the S-cis and S-trans is sort of like pseudo-cis and pseudo-trans, right? These are the same molecule, just different conformations, but these are the two most stable conformations of 1,3-butadiene. And the reason that these are the two most stable conformations is because in both of these, we can have the p orbitals in the same plane, and so we get conjugation when the molecule adopts one of these two conformations. When we twist, and so when they're not totally flat, then we can't line up the p orbitals like this, and so we lose the conjugation, and so that's less stable. And in fact, the energy that is required to switch back and forth between the two conformations is 15 kilojoules per mole. And interestingly, you may note that this is the same energy as the stabilization energy of the conjugated diene relative to a regular alkene. So what this is really telling us, when we go from the S-cis to the S-trans, right, we have to break up that conjugation in order to convert from one conformation into the other. And it makes sense that it's the same as the stabilization energy of the conjugated diene. And you'll also notice that the S-trans is more stable than the S-cis, and that's due to the fact that it has less steric hindrance. Right, the groups are able to kind of get farther away from each other. They're not bumping into each other as much. And if we look at this reaction energy diagram, again, for converting from one conformation into the other, the top of this reaction energy diagram, the transition state, is when the two pi groups are exactly perpendicular to one another. And so there's absolutely zero conjugation at the transition state here.